Good afternoon to everybody. I'm going to spend this time talking about something called Argo. So for anybody who's not familiar, Argo is an ocean observing program that consists of this whole network of floating instruments like this one. The floats are out there drifting throughout and continuously profiling the upper 2,000 meters of the oceans. And Argo is an international program that was started in part here at Scripps about 25 years ago, and it's grown into one of the most important sources of information that we now have about the global oceans. And the motivation for this project is related to current federal policies around artificial intelligence and how they're reshaping the funding landscape for scientific research, including for programs like Argo. So to try to illustrate the importance of maintaining support for Argo, I want to start by sharing some of why we need to observe the ocean in the first place. And I know it's a little bit late in the afternoon to be starting with the basics, but the Earth's climate depends on the overall balance of incoming and outgoing energy. And this means that the planet maintains a relatively stable temperature when the amount of incoming solar radiation is balanced by the amount that's reflected and emitted back to space, which is something that we've been observing using satellites for several decades now. But we've disrupted this balance by adding large amounts of greenhouse gases to the atmosphere. And our satellite data indicates that less energy has been leaving the system. We also have a record of temperature at the surface, and that shows a clear warming trend over time that you can see in this figure on the right. But the amount of surface warming represented here is only a small fraction of the overall energy imbalance. And all of the warming that we're experiencing at the surface can fit in that tiny line way down at the bottom that's purple. And the rest, all the blue lines represent more than 90% of the energy that's gone into the ocean. And you can see in comparison that the oceans have absorbed an enormous amount of energy. And this has significantly buffered the effects of warming that we'd otherwise be feeling in the atmosphere. But because of this, understanding what's going on in the ocean is central to understanding climate change. But this excess heat in the ocean also impacts our day-to-day weather. Heat that's stored in the ocean gets moved around by ocean currents, like the Gulf Stream on this figure, which carries warm water from the tropics to cooler regions, and by exchanging with the atmosphere, which influences storms and rainfall patterns. So being able to measure heat in the ocean and track where it's moving is essential for making the forecasts that we all rely on. But the challenge is that the ocean is incredibly hard to measure. It's enormous. We know it covers 70% of the Earth, and much of it lies thousands of meters below the surface. We have had reliable satellites for many decades now, but they can only see the surface of the ocean. And so to measure the interior, scientists have relied on ships. But the problem with that is that they're expensive and they require a whole crew to operate, and they can only sample a fraction of the ocean at a given time. These measurements are collected by stopping at stations along a transect that you can see on this map and lowering this platform of instruments through the full depth of the ocean. So it can take weeks to collect measurements along a single one of the lines that are shown here. And because of this, we were limited to only seeing a snapshot of the ocean interior at a time. And so this leaves gaps in both space and time. But that changed significantly when the Argo program started. And we've since gained the capability to observe the ocean continuously on a global scale. And as of May of this year, there are over 4,000 of these floats drifting around and collecting measurements that scientists aren't having to collect manually. And while Argo is not a replacement for ship-based data, the floats are able to observe the ocean in a way that wouldn't be possible using ships. So here are some photos of different Argo floats. All of them are engineered to autonomously move up and down in the water. And they all carry sensors that measure temperature, salinity, and pressure, which provide information about ocean heat and circulation. More recently, some of the floats also measure additional biological and chemical parameters like oxygen and pH, which are important for tracking things like low oxygen zones, ocean acidification, and carbon uptake. And most of the floats sample to 2,000 meters, which is a little bit over a mile. But the round one here in the middle is designed to withstand higher pressures and can dive down to 6,000 meters in order to observe the deep ocean. And a typical mission for a float looks a little bit like this. Once it's deployed, it'll drop down to about 1,000 meters and drift with the currents for 10 days. And then it will drop down to its profiling depth, so usually 2,000 meters or 6,000, before slowly returning to the surface and collecting measurements along the way. And then once it reaches the surface, it transmits this data by satellite and will begin the cycle again. And the data becomes publicly available almost in real time. And because of this, Argo's transformed our understanding of the ocean, not only from a scientific perspective, but also has improved our weather forecast by being able to integrate that real-time ocean observational data into our weather models. And one example of this is related to forecasting tropical cyclone intensity. And that is because warm ocean water is the fuel for a tropical cyclone. And that's why we monitor sea surface temperatures so closely when a storm is developing. But if we want to know how intense a storm can become, we also need to know how deep that warm water extends. And because as a hurricane moves over the ocean, it mixes the upper layers and it'll bring water up from below. So if there's only a shallow layer of warm water, a storm can cause upwelling of cooler water and it'll cause the storm to weaken. But if the warm water extends to greater depths, then it can continue drawing energy from it and it could intensify rapidly. So a recent example of this, maybe Zane remembers, was in 2024 when Hurricane Milton crossed a feature in the Gulf of Mexico called a loop current, which is characterized by very deep warm water. And in doing so, Milton strengthened from a Category 1 to a Category 5 storm within 24 hours, which is remarkable and incredibly fast. And predicting this kind of rapid intensification is still one of the biggest challenges in hurricane forecasting, primarily because it requires a good understanding of the subsurface ocean heat. And this is one of the reasons why Argo is so valuable. And research has shown that including this data in weather models improves hurricane intensity forecasts. And as Corey mentioned earlier, this is important because natural disasters like hurricanes can have devastating impacts on communities. And so better forecasts can save lives and allow coastal communities more time to prepare. And a similar concept also applies on longer timescales with El Nino, where because the ocean is slow moving, these slow changes in the transport of ocean heat in the tropical Pacific is one of our main sources of seasonal predictability. Seasonal forecasts provide information months in advance about likely shifts in temperature and rainfall patterns, which again allows communities a longer time to prepare. So the earliest signals of an El Nino begin below the surface, as this figure on the left shows. When an El Nino is developing, a deep pool of warm water that normally sits in the western tropical Pacific starts to shift eastward. And that heat eventually rises to the surface, raises sea surface temperatures, and alters atmospheric circulation, which tends to affect weather patterns globally. But because these changes begin in the subsurface, observations from Argo and other related observing systems can detect them often months before they show up clearly in the atmosphere. So these examples hopefully give you a sense of how uniquely valuable Argo data are. And for a little bit more context, many of our weather forecasts used to only look at the atmosphere, but the ones that we rely on today are increasingly coupled, so they include the ocean as well. And Argo data are the main source of that data, which ultimately means that Argo makes our predictions better. And that skill is especially valuable in a warming climate, where one of our best strategies is to be able to better anticipate what's coming. But that brings us back to what motivated this project, which is that funding for Argo is currently facing a lot of uncertainty. And this matters because while Argo is just one network that's part of a larger global ocean observing system, there's no redundancy. So interruptions to the Argo record can't be replaced or made up for by other systems. The US Argo program relies largely on funding from federal agencies like the National Science Foundation and the National Oceanic and Atmospheric Administration, which since last year have been facing significant disruptions like staffing cuts and grant terminations and a growing amount of uncertainty. And at the same time, artificial intelligence has become a central executive branch priority. And those agencies are increasingly expected to show that what they're funding aligns with AI. And because of this, the scientific community needs to be able to articulate why investments in Argo remain important and relevant even under the current priorities. So ultimately, the goal of this project was to understand and articulate how Argo fits into the current AI policy environment, and then to develop some materials that could help communicate Argo's relevance in that context. And to do this, I spent some time interviewing researchers across the Argo community to get a sense of how AI is showing up in their work, specifically trying to find out how they're already using AI and what types of AI-related work might grow out of the program in the future. But first, just to clarify what AI means here, in this context, it's referring to machine learning as an alternative to traditional modeling. Traditional models are built on the known laws of physics, so they solve those equations numerically to simulate how conditions evolve over time. Machine learning, on the other hand, learns patterns directly from data and then uses those learned relationships to make predictions. So machine learning methods can be much faster than traditional modeling, which is computationally expensive. And the takeaway here is that an AI model is only as good as the data that it's trained on. So one thing that came out of these conversations was that scientists in the Argo community are already using AI in a number of ways. In one example, AI is used to map sparsely measured variables like oxygen, which I mentioned was only measured on some of the floats, to produce monthly global maps, which turns this data into a much more usable product. And because oxygen is an indicator of marine ecosystem health, being able to monitor trends at this resolution is helpful for managing fisheries and other natural resources. And because we haven't been able to measure everything everywhere all the time, AI helps use all of the information that we do have by finding relationships between them, and this lets us do more with it. And so in a sense, it helps extract the most value from the existing data. Additionally, something that came up in conversations is that even though Argo has provided one of the most complete records of the global ocean that we've ever had access to, it's still a relatively small data set to the standards of modern AI. And so the growing opportunities to use AI here are limited by data, not by machine learning algorithms, which speaks to where investment might be the most impactful. And because Argo data is currently the best and most abundant source of that data, AI's capabilities in the ocean are directly limited to the degree that we sustain and expand Argo. But throughout these conversations, it was also noted that while AI needs good observational data, it lets you do more with the data that you do have, which means Argo's value is also dependent on using AI. And so there's a lot of synergy between them. And researchers identified additional opportunities to take advantage of AI to be able to do more with Argo in the future. The combination of data being collected every 10 days and available almost in real time, together with the speed that AI lets you do things that were previously computationally slow and expensive, means that Argo can help us get closer to monitoring conditions in real time. And there is a whole range of applications for that, from fisheries and making fisheries more sustainable, and to being able to make more localized forecasts for coastlines, to Ella mentioned marine carbon dioxide removal. Data from biogeochemical floats could be used to verify that the intervention is working as intended and not causing inadvertent harm to ecosystems. But this is, of course, contingent on Argo being funded so it can be sustained and expanded. So with that, to zoom out a little bit, one of the takeaways for me is that we tend to assume that our ability to predict and understand the Earth system is going to continue improving over time, because it has. But the reality is that this has only happened because we've continued to invest in the resources that make that possible, which is this whole integrated observing system. And while the push at the federal level for AI right now is motivated by accelerating scientific progress and maintaining global competitiveness, it seems like it will be hard to achieve meaningful advances in AI without funding the core systems and the science that give AI something grounded to learn from. So the hope is that this project might be a small contribution to this in helping maintain support for Argo. And with that, I would like to thank my committee, Dr. Sarah Gilly and Dr. Corey Gabriel, as well as the many others who offer their time and thoughts throughout this project. And thank you all for being here.
Actually, I have a question for you, Chrissy.
Sure, Jada.
Would you like to talk a little bit about the products that you ended up with for your project?
Sure, yeah, I wrote a couple of white papers. One of them was intended for program managers at the funding agency, like at NSF. And there's a meeting next week for the US Argo program, and hopefully it will be distributed there, and it'll be kind of the start of a conversation for the folks to have. And the other one was just more of a general kind of government relations deliverable type.
Very exciting. Thank you.
Thanks.